So Olivier Desjardins from Cornell, and he's introduced me several times.
Yeah.
I was one of his first PhD students.
Like officially number 3, and then you ended up graduating in number 2.
Yeah. That's great. Yeah. So take that for what it's worth.
Yeah.
And so it's my first time introducing Olivier. So Olivier did his master's in France and Tupero, and then went to Stanford, did a master's PhD at the Center for Turbulence Research, working under Heinz Pitch. Was supposed to work on combustion and decided he felt like he could take growth instead. And a lot of Olivier's research is on numerical methods, trying to get formal conservation, high order convergence when you have interfacial flows, gas-liquid flows. But he's also done some work on other applications. I think this talk will primarily focus on recent state-of-the-art in terms of simulation and modeling for gas-liquid flows. A lot of applications are relevant to atomization processes. I guess a fun fact, Olivier's the only person I know who started rock climbing after he left Boulder, Colorado, several years after. So I met him when I started my PhD at Colorado, and that's where I learned to rock climb, but I guess you had to leave and then. But with that, I'll leave the floor to you, and thanks again for coming out. Oh, one announcement. So this is a joint MICDE mechanical engineering seminar. If you're not already signed up to receive the MICDE announcements, there's a number of exciting seminars and talks coming up. So next week there's a symposium with a lot of good talks, and I think Los Alamos will have several talks the following week. So please sign up and get more involved if you're not already with MICDE, because this is just one of many exciting big talks related to computational discovery and engineering. So thank you for coming, and I'll leave this floor to you.
All right, thank you. All right. Is this working? Can you hear me? Okay, cool. So thank you very much, Jesse, for the kind of introduction and for making fun of me a little bit regarding my rock climbing experience. It's all fair. And yeah, I see a lot of faces I've met during the day. It's been a very nice visit. It's been exciting. Lots of good work going on here, and yeah, it's been a great day. Okay, so I'm going to talk to you indeed about. So I guess I'll just mention one quick thing. So Jesse mentioned work we're doing to improve conservation, ensure conservation, and go towards high order. So in the context, so we're looking at liquid gas flows. So that means we have discontinuities. In the context of discontinuities, high order for me will often mean second order. Okay, so let's set the stage clearly. For those of you doing DG, for those of you doing like uniformly high order methods, being second order in the presence of like a true discontinuity, like for the density in the gas here might be 1, the density in the liquid might be 1,000. Maintaining second order accuracy here is already a pretty big challenge. So I'm starting by lowering expectations so that you don't get too disappointed when I tell you, hey, we're second order. Okay, so I'm gonna talk to you about, let me say a few things about the title briefly. So we'll talk about, I'm realizing that this pointer is not going to be very helpful. So we'll talk about a little bit of the story of that simulation in a sense. So I'll tell you how we're simulating sprays. And this is a specific example of the formation of a fuel spray relevant to gas turbine kind of applications. It turns out it's a really hard problem. Probably everyone telling you the work they're working on, they tell you that it's a hard problem. This is really a hard problem though. So we're gonna talk about some of the work we've been doing to improve the numerical backbone of our codes in order to make it possible, in fact, arguably pretty easy to model the topology change, meaning the breakup in those type of liquid gas flow simulations. So we want to predict the formation of drops. That means that we want to be able to predict how a drop will separate from liquid jet or liquid core. And we want to do that in a way that's physics-based and not entirely polluted by numerical errors. Okay, so that's kind of the story I'm going to tell you. The multi-scale aspect will come towards the end. and hopefully this will be convincing enough that, oh, of course, this meeting is being recorded. Okay, got it. And now, okay. I should have control again. Perfect. So I'm going to start with quick acknowledgements. This work has been mostly conducted during an ONR Muri project that's now complete, finished about a year ago. So a lot of these ideas were started during this program, and that funded a number of PhD students, Rob Cody, Lam Vu, and Austin Han is finishing his PhD on some of those ideas. And there's been also funding coming from industrial partners through the IFPRI consortium, and that's helped interactions with a couple of students, Lorenzo Bruni, and I guess Fabien Evrard is a Marie Curie postdoc visiting, spending a couple of years in Cornell to work on some of those ideas. Okay, so that's some of the key people. Let me start by telling you why we care about atomization, so the breakup of liquids. We care about that because it turns out most flows around us, whether they're environmental flows or relevant to environmental processes or engineering processes, end up being multiphase. It's kind of the standard thing. A lot of the CFD we do is single phase, but that's because we typically make simplifying assumptions. The reality of a lot of the engineering processes around us involves multiple interacting phases. So walking you through some of those things, this is the well-known series of videos by Buriba's group that became very popular during the COVID pandemic, looking at the dispersion of aerosols and the transmission of respiratory diseases. That involves the breakup of a spray. It turns out it's interesting for multiple reasons. It's coupled to the internal shape of the flow passages. And it also involves complex fluids, so it involves non-Newtonian processes. This illustrates the idea of fuel injection inside scramjets. If you have a really fast flying system that's powered by a scramjet engine, you have very little time to inject your fuel, atomize it, evaporate it, burn it, because the residence time is minuscule. And so there's more things we could say about that. If we go down here, this is your standard gas turbine device in the back. So this is what most of our commercial aircrafts fly with. Here we typically want to optimize the operation of those engines. We want them to pollute less, to be less noisy, to be more safe. A few more examples. We're spraying here pesticides. So the agricultural type of applications is pretty important. Here we have a couple of examples involving powder production. So if you want instant coffee or your cocoa powder, that was probably produced in a spray dryer. So there was a slurry that was generated, a mixture of particles and some sort of a liquid, and that's sprayed in a collection of drops, and then that's heated up such that the water evaporates, and you're left with those little, like this powder. Another way of producing a powder is if you're interested in additive manufacturing, you need large quantities of high quality, well-controlled metal powders. You do that by atomizing a liquid metal. So you heat up a liquid and atomize it, typically by peeling it off with a high-speed flow of gas. So again, atomization. If you want to produce pharmaceutical granules, or if you want to coat your whatever pharmaceutical products, that typically would involve spraying as well. And okay, I'm spending a lot of time, but one last example here. One of the key parameters in climate modeling is the interfacial exchanges between the ocean and the atmosphere. And part of that involves a prediction of sea sprays. I don't have a good application for this thing. All I'm saying is I've been trying to raise funding to predict this, and it's not been successful so far. But anyway, that's another example of some sort of atomization of also very much non-Newtonian liquid. Okay, so more specifically, if we think about fuel sprays, which is like a subset that's been of interest to me and my group, fuel sprays matter a lot because we need, so when you're operating a gas turbine, you need to evaporate your spray, and you do that by increasing the surface area. So you're spewing out liquid very highly density, energy dense, and then you're going to break it up into droplets, and those droplets are going to evaporate, and it's going to give you a flame and all that. So if you want to predict properly the stability of your flame, how much NOx you're going to be producing, and understand something about combustion efficiency, all that involves being able to say something cogent about the drop size distribution you're going to generate. And it turns out we struggle to do that computationally. And that matters a lot because in fact, most transportation areas are seeing a reduction in the production of CO2. The only one that's not is the air transport area, which is seeing a pretty constant, well, COVID was a bit of a change in the slope, but we've been seeing a constant growth in the CO2 coming out of air transportation or emissions. Okay, so we're interested in simulations of this. There's lots of very interesting work being done with experiments, but ultimately we want to do. Did this thing turn off? I feel like I'm hearing myself less. No, that's very good. Okay, we're interested in doing computational modeling of this type of process. So it's going to be a high-level slide. That there's a few messages. The oldest thing I'm showing here is 2013. So in the past 10 years or so, you're starting to see high-quality, high-fidelity simulations of turbulent two-phase flows that are aiming at predicting a drop size distribution. Here, it turns out you can't really see it, and I'm going to use a laser pointer, which you're not going to see either, but that kind of, maybe you can guess where it is, but I'm pointing here to those little red lines here. Those are, in fact, resolved interfaces. So those are little liquid jets that are coming out of nozzles, and they are breaking up and forming a whole lot of drops. And I don't know if you can make out the little black dots downstream. Those are all the droplets that have been generated. So this is an extremely multi-scale simulation, lots of computational resources to try to predict in a semi-realistic, like pretty complex geometry, the drop size being generated from in the fuel injector. A couple of other examples from a few years back. There's some work here that shows a pressure swirl atomizer. So you're taking a liquid, you're spinning it out into a cone, and then it breaks up into a collection of drops. And then here, one thing that I'm emphasizing is the fact that ultimately those methods tend to aim at generating a collection of drops. And those drops are typically going to be represented as point particles, so a large collection of Lagrangian objects. And here you can see those Lagrangian, well, again, I'm pointing, you can see those Lagrangian objects as all those little dots that have been generated. And then we can process that, assess the size distribution, et cetera, et cetera. So another example right here from last year. And then one more example here where you see a flapping jet that is forming ligaments. All this is tracked on the mesh, and ultimately we're getting all those little colorful spheres are the Lagrangian droplets that have been generated. Okay, so high picture ideas here. Using standard CFD kind of techniques where you have a mesh that discretizes your domain and on which you solve an evolution equation that allows you to track where your liquid gas interface is. Those type of methods, Eulerian interface capturing methods, have at this point reached quite a bit of maturity. We can do those simulations and apply them to pretty complex situations. Those simulations are now, at least in the past 10 years, I'm showing you a few examples here, those simulations are now being used in order to specifically extract drop sizes from first principles. And the standard practice that I kind of hinted at is to do Eulerian-based interface capturing. So you're following the evolution of an interface on the mesh. And then once a drop is separated, you're going to say, all right, I'm not going to spend as much resources tracking this. I'm going to convert that to a Lagrangian drop. It's now going to be a point that's going to evolve according to a set of ODEs instead of complex PDEs. So that's kind of the go-to approach. Eulerian method to track the interface, and then we transfer the broken drop to a Lagrangian representation. Okay, why am I saying all this? Well, because I want to, this thing is falling apart in my hand. Because I want to show you how this works in a case that we've done in my group. So we're going to focus on an example of a gas turbine type fuel injector. It is often the case in gas turbine engines, we're going to make use of a fast flow of gas to atomize our liquid. Now, if you're flying very fast, you have lots of fast-moving gas available. What you don't really want to have is carry the tools to pressurize a liquid, right? If you're, however, driving a diesel truck, it's sitting on the road. You can probably carry around the weight of the equipment required to pressurize your fuel line. However, you don't have a lot of fast-moving gas available. That's kind of the trade-off. So if you are looking at what's going on in the plane, you're probably going to be using a fast gas to break up the liquid. So the scenario here is a slow-moving liquid fuel coming through the center pipe here, and we're going to have a fast-moving co-flow of gas around it, and that gas is just going to peel off the liquid. Looking at conditions, we don't necessarily need to go into the details here, but we're looking at typical conditions for what I'm going to show you, which correspond to one of the key operating conditions, which is the engine restart at high altitude. You have engine failure, you're flying, everything is cold around you, and you need to restart the engine. So that means that typically the density ratio between the liquid and the gas is going to be pretty high. The Weber number, which is a number that characterizes the ratio of inertia to surface tension, is going to be pretty low. So you don't have, your gas doesn't have a lot of oomph to move things around. And your Reynolds number is, a few tens of thousands, definitely turbulent, but not necessarily enormous Reynolds numbers. Okay, so with something like that, I guess I have a little bit more information. Hopefully you can see that. It might be a little bit too bright to completely make it out, but this is a video of the experiment at the conditions I'm listing above here. So, this is a bit more details for those of you who are well versed into this area. Otherwise, it doesn't really matter. There's some operating conditions. You can see the complex liquid spray being formed, and this is our simulation of it. Hopefully that looks reasonably close, and if not, it's because it's too dark. Nothing else. So let's spend a bit of time on this. Actually, I forgot. I thought I should include some equations. So that's going to be very limited. What are we solving? We're solving Navier-Stokes in a two-phase environment. So we're going to assume that we can solve our two-phase flow problem using a single velocity field. We're going to assume an incompressible flow, isothermal. Our mass conservation tells us that the flow is divergence-free in both phases, including also at the interface. That's what our Navier-Stokes equations end up looking like. I'm not going into details here. I'm just hinting at the fact that this subscale term here means that we're going to be doing a larger dissimulation. So might be more details than necessary. There's a little bit of modeling for curvature effects at walls. Again, we're not going to go into details here too much. The big idea is we need to track where the liquid-gas interface is, and we're going to do that by solving for the evolution of a liquid fraction field. So we're going to call that alpha. And that's going to evolve in time because it gets advected materially by the flow field, right? That's what it is. So this alpha here represents the fraction of each of our cell that is filled with liquid. So if I'm sitting well within my liquid jets, this value is 1. If I'm inside the gas, this value is 0. In between, it's going to be somewhere between 0 and 1. All right. From that alpha, I can extract a density for my cell. And I can extract a reasonable closure for my viscosity in the cell. And then I said that we'll ultimately transfer our broken up droplets into Lagrangian representation, and here we'll solve Newton's second law, basically track those points. Okay, just a tiny bit of it. Oh yeah, go ahead. No, so the way we're treating that is we're saying that this is really only an LES as far as the gas is concerned, and the liquid is slow moving enough that this term goes to 0. So we're kind of ignoring something that is clearly not, it's not irrelevant, but here we're basically saying that that's a closure we only need in the gas. That's a good question. That's not an unsolved problem in general. All right, so just a tiny bit more on the underlying methods. So for those of you who have been exposed to those ideas before, what we're effectively doing here is what's called a volume of fluid method, VOF. Volume of fluid method is a geometric way of moving an interface around by transporting the amount of liquid that's in each cell. So if you have a field of alpha, so that full blue here might be alpha is equal to 1, that's alpha is equal to 0. And so this is fully liquid, this is fully gas, and in between is somewhere between liquid and gas. The first step is going to be that we're going to try to build from that a representation of where our liquid-gas interface is. Okay, so that's a closure step. That's a step where we say, I know my distribution of volume. From that, I want to represent a reasonable looking interface. And we do that using a method that's been proposed, I guess, actually the year I was born. So back in like well, maybe just after, but 1982 or so, I think, was when Young's proposed that. So the idea we're going to use here is what's called PLIC, piecewise linear interface construction. So each cell is given a planar interface. Okay, it's allowed to be discontinuous from cell to cell. And if you're fully liquid, you don't need an interface. If you're fully gas, you don't need an interface. From this representation, you can then go about and do your transport. And maybe the simplest way of doing that is to do some sort of a Lagrangian remap kind of approach. You take that cell, transport time, and figure out how much liquid, how much gas it had back at the previous time step. And then you deposit that in your cell at the new time. You have formal second order accuracy, exact conservation. I'm skipping a few things, but for the most part, if you work hard enough, you get those things. One little detail here is there's an interesting hidden optimization problem. Figuring out what is the proper place for this interfacial plane, given the distribution of neighborhood volume fractions, is not an easy problem. There's a number of solutions that have been proposed. We're going to make use throughout this talk of a couple of different things, but one thing that will be recurring is the so-called Elvira method, which is like literally a multidimensional optimization exercise. We try to find the plane that is optimally fitting a local region of cells. Okay. So that gives us an instantaneous field that looks like that. And I'm going to be showing you simulations, actually one simulation at first. It's not an enormous simulation, about 30 million cells, 200,000 core-hours. So keep that in mind, we're not breaking the bank here. The data that I'm going to be comparing against comes out of University of Washington, specifically Alberto Eliceda's group. And back then, his postdoc was Nate Mashikohen, I should say. And then Ted Heindel at Iowa State University. So some qualitative comparisons first. Again, I'm concerned that this black background was maybe not optimal, but you can see kind of a flapping jets. You can see that flattening of the jet. This jet kind of ends up inflating into a bag. Droplets are created. Fork-like shape is left behind on the rim of that bag. Yes. Yeah, this is actually uniform Cartesian. Yeah, it doesn't have to be that, but this is what we're doing here. Yeah. And so, you know, qualitatively, things look pretty similar. I can compare the flow coming out of the nozzle here. So there's a turbulent gas flow coming out of this annular nozzle. We can compare the distribution of, we can compare the mean velocity between our simulations and the hot wire experiments. What we're finding is, especially right above the liquid, we seem to have a pretty good handle as to what the mean velocity as well as RMS looks like. Then we can take all this and bring that to Argonne National Lab and put that in the advanced photon source and illuminate this with ultra-fast X-rays. And we can do that with a monochromatic beam, which allows us to directly get from the light intensity a measure of the length of liquid along line of sight. You can raster scan this entire thing, and that gives you a direct measure of how much liquid on average is present everywhere in the domain along a line of sight. That gives us a map like this, which is perfectly quantitative. There's no modeling assumption here. So EPL here stands for equivalent path length of liquid. So this is, again, line of sight. If you normalize that by the exit diameter of the liquid, the value here should be 1, and that's what we found. And then we can extract profiles from that and compare to our simulations. So along the center line, and then along radial profiles. Again, the point is not necessarily to go into the details here. Things overall look pretty good. We can look at RMS profiles. They also look pretty good. So overall, we're pretty happy with all this. And we can keep on pushing, try to look at some information about how far the jet extends before it breaks, how wildly it flaps. So we can extract both what we call the intact liquid length, LB, down here, And we can look at the flapping frequency by doing a Fourier transform of the lateral motion of the center of mass of this thing. And we find that the full distribution of the intact liquid length matches extremely well with the experiment. And that the dominant frequency, actually, I think the number is here, is within like 12, 13% here. So overall, again, the general picture is all this looks like it's working pretty well. And I would argue back to when I was starting to talk about the different methods, we're basically at the point where the methods have reached quite a bit of maturity. We're exploiting here formal second order accuracy, exact conservation of volume, and since we're in compressible mass as well, and exact conservation of momentum in those simulations. We have pretty good ways of estimating the curvature. We're formally second order accurate for our transport of our volume fraction. If we differentiate that twice, we can't ever be converging for curvature. That's not possible, but we can ensure that we have low enough errors, and that's basically what I'm saying here was near converging. And all that with, again, 200,000 core hours, not very expensive. So in general, that works pretty well. However, we cared about all this because we wanted to do drop size statistics. Oh, sorry, go ahead. Yeah. Yeah, it's exactly bounded. Yeah, formally bounded, formally conservative, formally second order, which is where we spent actually quite a few years to get those properties. The number of schemes I've had, like 2 out of the 3 for many years. And so we have like a series of like ways in which we do that. I need to say this. The formal here is that is a little bit of an overstatement. In order to get exact conservation, we locally, in typically small ways, modify our fluxes in a way that shouldn't be formally second order. However, we've not been able to measure this in any test case. So formal is not, it's an observed second order. The formal accuracy is effectively lost by enforcing strictly conservation. So that's a bit of an overstatement. In case you're wondering, hey, some things got to give, yeah, a little bit. So I'm yeah, all the finite volume remapping flux base that you've probably seen from Mark originally and a few other people. Yeah. Do you know this is we're just the statement I made here is just the fact that the momentum is conserved, or at least the momentum conservation is not affected by the density ratio aspects. Okay, so I am not making any statement regarding surface tension, although surface tension is written in a CSF type of approach, which for exact curvature or with constant curvature would be exactly momentum conserving. It is not an energy conserving implementation, however. We've been hunting hard for this and we haven't been able to find that. Okay, so the point of all this was to say, yeah, it looks good, but actually if you look at the drop size statistics, which we set out to produce from those simulations, the story changes dramatically. In red here, you have our PDPA experiment. I'm saying our, it's from University of Washington, Alberto Eliceda's lab. And then we can do some math refinement, but you can see that, yeah, maybe it's going in the right direction, but it's not there. Yeah. Yes. So we're resolving the drop using this volume of fluid technique. So when we generate the drop, it's actually on multiple cells, and then we convert it to a point particle approach, where we send it. So we know its volume by we know the volume of the region, and we can compute the momentum in that droplet. We can compute. Yeah. So there's a number of assumptions there that tell us, okay, if it's too stretched out, it's not going to be a drop. If it's spherical enough, okay, we're going to call that a drop, and it needs to be small enough as well. Yeah, there's a few things that I'm not really mentioning here. But anyway, this is a bit of a disappointment. That suggests that we can't really predict what we want to predict. And part of the reason why is if you look at simulation compared to the experiments, you can see the presence of those thin membranes that you can infer to be on the order of a few microns that are not necessarily that surprising. You're blowing on a sheet of liquid, you're kind of inflating a little bag out of it. But the issue is that our mesh is not resolving down to a few microns. And so what we see is breakup. And that's purely numerical breakup. It looks good. It generates a collection of drops, but they're too large and we can't predict the small enough drops. So we don't have the small drops that we should have, and we have instead way more larger drops that are controlled by the mesh size. Okay, so we're not doing that good in terms of predicting breakup. Do we do better if we simplify the problem and we look at an individual droplet? Well, it's actually a very easy, well, I shouldn't say very easy experiment to do, but it's not a very hard condition to achieve. If you blow on the droplets in a crossflow, it will inflate into a bag and burst, and you get back breakup like this, and you'll have left over a rim that will undergo Rayleigh plateau breakup, so a few large drops, and then you have a large collection of very tiny drops controlled by the size of the film. We can throw that in a solver and get what looks like garbage. So, you get that drop that starts flattening. So this is kind of a side view. You see the drop that starts flattening. I don't know if you can see that the film is starting to look noisy here. And then when you get this ring with like 3 drops or something, that's with about 13 cells across the diameter. Not an enormous amount of resolution, but there's not much going on in there. But that kind of emphasizes the fact that, yeah, certainly we can't hope to resolve this like that. We can throw like a factor of 3 or so in the resolution. You get something that maybe looks a bit better, but it's still far off. So of course we can just keep on refining. And here I'm showing that from the perspective of drop size PDFs. They're just like all over the place. Doesn't match at all with the experimental PDF that you see in the histogram here in gray. So now you can say, what if I were to just hammer this thing with resolution? And I'm not too excited at the idea of doing that, but some other people are. And specifically, Senli Ling has done like some really beautiful simulations using the code Basilisks, which is an AMR code that allows to throw large amounts of resources along this thin film. And so it's able to reach an effective resolution of about 2,000 cells per diameter, like an enormous amount of resolution for this problem. That represents about 4.3 million co-hours for the breakup of a single droplet. And the conclusion they reach is that the breakup is still numerical. So it's going to be a hard problem to solve by just brute forcing our way through this. Okay, that's kind of the message I want to get to here. This is a film. You might say, well, maybe a ligament, right? Fundamentally, you're trying to change the topology. So you have an interface, you want to fold it to the point that you can separate the drop. You can do that by folding it in 2 and form a film, or you can do that by folding it in 2 directions simultaneously, form a tube, a ligament, and then ultimately you need to pinch off the drop. So that's one mode. Films are hard, okay. What about ligaments? Well, it turns out there's some work that's been done by Marco Arienti at Sandia about 12 years ago, going all the way down to molecular dynamics type of approaches to understand how ligaments break, liquid ligaments break as they get pulled on. And what he found is that the physics are rich and complex as you go down orders of magnitude in terms of resolution. So as things become smaller and smaller and thinner, there's still new things happening. So if you want to be in what we call in fluid mechanics the limit of direct numerical simulation, where everything is resolved, it's going to be incredibly expensive. So it's not even much easier to think about ligaments. All right. So why does all this happen? Well, it happens because we make numerical errors. If I want to represent a thin film like that using my volume of fluid method, here, one thing that's going to become obvious is that I'm going to break my film simply due to the assumption of having one interface per cell, right? What we call PLIC, the piecewise linear interface construction assumption, is going to break things automatically. And I think it should play automatically. I can show that. Actually, let me go back here. I'm going to put a thin film of liquid into a stagnation flow. And you can see this process in action. My assumption of a single interface per cell prevents me from emitting this film. That sounds probably reasonably obvious. So that's going to generate a collection of droplets of about the size of the mesh. It's all wrong, right? It's entirely numerical errors. This is specifically done in the context of pretty much all methods which will suffer from something like that, whether it's level set or diffuse interface methods. Surface tracking does not explicitly suffer from those type of issues, but it suffers from other related kind of issues. So ultimately, you're going to have to struggle with this no matter what. All right, so how do we fix that, right? Ultimately, the point is to go beyond those numerical issues. And so I'm going to show you two ways in which we've been trying to fix this. One is maybe the most obvious one, which is to say, if what makes a film break is the assumption of a single plane per cell, let's put 2 planes per cell, right? So is it an easy thing? Well, yeah, kind of. It's making the optimization problem of finding where the plane should be a little bit more complex, but not enormously so. So it's really, I would argue, the most naive strategy. So we're just going to reconstruct our interface using 2 planes. We don't necessarily want other people to bother redoing that, so we are offering it as an open source library. So if you're interested, you can look it up. And then, we've chosen a way of representing that. So there's, 2 planes means we have 2 normal vectors. A normal vector is 2 parameters, 2 angles, if you will, and then you need a distance to place them. So that's 3 parameters per plane. So you have 6 parameters. So you're optimizing into a 6-dimensional space. We're representing that using the following parameters here. So we have a shared normal orientation, and then we can open up or close up our interface, and then we can position our planes to ensure exact conservation. Okay, this thing is not necessarily, we're now in 6 dimensions, we want to have enough data to make sure we can optimize this properly. Optimize this properly. So we're going to make use of volume fraction information in a 3x3x3 stencil. We're going to make use of phase barycenter information, so we can look at not only the zeros or the moments of our phase in the neighborhood, but we can also look at where, so the first order moment of our phases in the neighborhood. So we can say how much liquid, how much gas, where is the liquid, where is the gas. We can add to this also surface moments. How much surface area do we expect to have? And we can put all that as an inductive function for an optimizer. We use a Levenberg-Marquardt, do a little bit of data analysis based on a k-means, spherical k-means algorithm to generate a high-quality initial guess. And then we go through our optimization, and that gives us our reconstructed planes. Yeah. So the idea of those 3 planes here is that this is the data that gets advected in. So from the previous time step, we can advect our surface in, and then we can say, all right, if I have those 3 little chunks of interfaces that have been brought in, how do I best represent that? Should I use a single plane like here in blue, or should I maybe, if instead of having those little 3 planes, I had 1 plane coming from here and another one from here with opposite normal orientation, the algorithm will conclude, oh, I need 2 planes to represent that. So that shows the available data. Yeah, but that's a good question, and I understand why it would be confusing. Okay, so we can put that in a little toy problem of our stagnation flow, and indeed, we fix the problem. Our interface doesn't break, the field is maintained. So in practice, what we've done here is we've changed just the key parameter that was, or the key step that was messing up everything. We've modified it, enhanced it. The cost increase is pretty limited. So we do that only in the cells that necessitate it, right? So in general, most cells are still treated the same way. It changes pretty much nothing about the rest of the algorithm. So we maintain exact mass and momentum conservation. We don't really modify anything along those lines. We maintain second order accuracy. And then we can essentially remove numerical film breakup. Ligaments don't look that good. Representing the ligament with 2 planes is a little wonky. So we've been thinking about maybe doing 3 planes, but it's a little bit dirty. But as far as films is concerned, it seems to be addressing the problem fully. Okay, so now that is one strategy, and I'll show you what we can do with this in a second. For now, I'll just jump to the next step, which is, okay, maybe this is a bit naive. We're just putting 2 planes. This is really the path of the future. The other thing we've been thinking about is, instead of putting 2 planes, what if we were to uniformly increase the accuracy of volume of fluid methods? What limits the accuracy of volume of fluid methods is this assumption of a planar reconstruction, planar interface. The next logical step would be to have a paraboloid. And if we do that, we can actually do a lot of things that are pretty cool. So the second idea that we've been pursuing, and that's we actually just recently got a paper out on how to do this, is to go to a paraboloid interface within each cell. So paving the way to third order VAR for the first time since the Plick type of strategy was proposed in the early 80s. So it's been like over 40 years that we've been stuck with second order. How do we actually go to third order? So we're going to call that PPIC, piecewise parabolic interface construction. Again, it's all implemented in an open source library. And it's kind of an interesting approach. The idea is to have very, very fast ways of intersecting a cell, grid cell, with a paraboloid. You want to be able to calculate exact moments of the capped cell by a paraboloid, okay? And the way we do that is by doing successive application of the divergence theorem to replace the volume integration by ultimately a collection of 1D integrals that can be partially analytical, and some of them need to be numerically approximated, and then we can find a couple of ways to do that. But essentially, we replace the integration over that complex volume by the integration of a few 1D integrals over either straight lines or conic section arcs. So the math ends up working out pretty easily. And what you end up with is a method that can preserve exactly your volume fraction, so exactly conservative, but gives you a third order reconstruction. And now, if you have a paraboloid, you can choose coefficients such that this paraboloid might look locally in the cell like a sheet. Or so just like one high curvature or one high coefficient in your second order term will give you a flat sheet. Two high coefficients will give you a tube-shaped object, a good model for a ligament. So now your reconstruction directly embeds or enables the idea of representing subgrid features. And again, the idea here is that this is still fully compatible with standard solution masses. It's still exactly mass and momentum conserving. We haven't really changed anything there. The cost increase, so we've analyzed it. We've been able, so my postdoc Fabien has been able to optimize this to the point that it's 6 times more expensive than Plick, so it's more expensive. Okay, but it's not like orders of magnitude more expensive. It's still definitely doable. But again, you have third order accuracy. One consequence of third order accuracy is if you look at the magnitude of the spurious velocity generated when the droplet gets transported in the flow field, that's what you get from Plick, and that's what you get from PPIC, from this paraboloid reconstruction. Everything is overall more accurate, more stable. And then there's still a lot of work to do here, but in theory, we should be able, with the same reconstruction strategy, to generate thin ligaments, subgrid scale ligaments, as well as sheets. So that's something that's still work in progress. We're trying to build that into the natural solution of the algorithm, but there's still work that needs to happen here. Okay, so now, oh, sorry, go ahead.
How are the neighboring cells treated? Is there zero continuity between the?
No, so it's piecewise. So it's done at the level of, so as we go high order, we could try to do that. The issue of doing that is it makes the problem global. And so we've toyed with global optimization to minimize the gaps between cells, but it tends to be expensive and we haven't really found ways to make it worth it. It's a really valid question. It's something that if we could find a way to do that really efficiently, even just like partially solving this more global problem, I think the methods would get quite a bit better. But
I was just wondering, what is the impact of having, say, a linear reconstruction within a cell versus having a piecewise, right? So,
yeah, so we find that the piecewise reconstruction almost entirely closes the gaps. It's I could have shown that it actually may be partially visible here. I don't know if you can see. You can kind of maybe make out that there's little facets and little holes, little white dots around here. If you were to stand where I am, you would see that. Here, you don't see any of that. It's actually almost perfectly closed. It's not, if you zoom in enough, there's a gap, but this reconstruction mostly, enormously reduces the discontinuity. But yeah, we're not trying to do that. So the most general shape would be a quadrix. but that would be harder to do. We would not be able to assume that everything is at worst a conic section arc. So really the main thing we wanted is something that can require the approximation of conic section arcs, which the paraboloid would do that. So ease of integration is what led us in this direction. Okay, so we forgot to talk about physics. Let's talk about physics a little bit. So we have now those enhanced VOF methods. So that's, I would argue, delays the catastrophic numerical errors leading to bursting films for purely numerical reasons. This does nothing to model a drop size distribution. It does nothing to capture the subgrid scale physics that are going to happen on those films and subgrid scale ligaments. We're just representing the shape. We're not solving the right equations. It's still at the subgrid scale. So we're going to need now to start thinking about physical modeling of the flow within those ligaments, those sheets, and how they break. But the argument here is now we have delayed this catastrophic onset of sudden breakup. So if we understand something about the subgrid scale physics, we can start reintroducing them via models. And the argument I would like to make is if surface tension is strong enough at our subgrid scale, well, we probably know quite a bit. So, a single ligament will undergo like Rayleigh plateau. We know kind of how to predict that. A sheet will have some thin film dynamics that we kind of understand as well. So we actually have quite a bit that we can say about those things. So one thing we need is to be able to identify those objects. So we need to start. So I've kind of been talking about films and ligaments. It turns out it's not easy to convert what we kind of see with eyeballs when we run simulations into the ability to say, all right, I have a ligament here and it extends from this region to that region, encompassing all those cells in, in the way. So we have ways of doing that. This is mostly based on fairly well-established connected component labeling techniques. So we have a way of on the fly processing things and say, all right, I have a film here. I'm going to need to have a film model that kicks in at some point. Oh, I have a ligament here. I'm going to have a ligament model that kicks in. So assume that this is available. It's not actually that hard to do, but this was a necessary step. Okay, and from that, we can start playing with subgrid scale modeling. And I'm not going to show you like a complete story where everything works. I'm going to show you a few little bits and pieces showing that we're actually enabling things that have not really been possible before. So here, using this reconstruction with two-plane in our VOF scheme, we can start looking at coalescence issues. So it turns out that two drops, when they come together, even at fairly low speeds, could either merge or they could bounce off one another, depending on whether you give enough time for the gas film in between to drain or not. If you take any standard VOF scheme, it will always predict breakup, coalescence, always. Because once the two drops fall within the same grid cell, they automatically will be merged by pretty much every scheme out there. So it is not possible to predict the bouncing of two drops using a single VOF field using standard techniques. But now with our simulation technique, you can see here on the top, that's actually the default behavior. If we want coalescence to happen, we need to say, hey, this film should break. And so we can do that here. I'm using a model proposed by Quaker et al. 10 years ago or so, which is a simple timescale-based argument. So it's an argument that says, if the film has had enough time to drain, then it should merge. And that's enough to make it work. 5 minutes, yeah. So that's an example of coalescence. We started off talking about this bag inflation in the drop. We can start looking at that a little bit. So this was our standard Elvira Plake kind of method, showing that essentially this numerical garbage. If I turn on two-plane reconstruction, you're seeing here a side view. So that's the rim of the drop, and here you can see the bag being formed. You can see we're forming a stable bag. But again, there's no physics in there. So if I want this bag to feel the effect of surface tension, I need to reintroduce that, because at this point, this is completely separate. So I can do that pretty easily by saying, well, I actually know the shape of the bag. I can compute the curvature on both sides of my film, sum it up, and apply it directly as a pressure jump between the gas inside and the gas outside. If I do that, I'm now accounting for surface tension, and I slow down drastically the inflation rate of my bag. Okay, So that's just a quick illustration of this. And then the next step is to say, well, we set out to do breakup. It turns out there's a couple of models that exist that have been proposed. There's a very recent model for film breakup that's part of a bigger machinery of aerodynamic breakup modeling for droplets, proposed by Jacques and Ashgriz last year. And that model is, I can give you the general idea. This model looks for when the film, so this is a model, entirely algebraic model that was built as a companion tool for experiments. There was no simulations involved. What they said is that in their simulations, they saw breakup happening at about a film size of somewhere between 1 and 2 micron. And then they saw typically drop size distributions that looked like a gamma distribution, and they have a couple of parameters to make it kind of work. And so they published that along with a lot of other things, and that gave pretty good results for predicting drop size in this kind of back breakup scenario. And a couple of years before, there was a ligament breakup model based on Rayleigh plateau instability proposed by Kim and Moyne. And so we can just like literally apply this as is, like drop into our R2P model and use that to perform breakup. So now this is, we've removed the numerical based breakup of our thin film, and we reintroduce now physics-based breakup model. And here I'm only comparing the drop size distribution in blue coming out of the film, and that should match, or should be compared with this first mode of that PDF. So that's data coming out of Gildenbecker et al. When he was doing his work at Purdue. This first mode was identified as being due to the breakup of the bag. And you can see that we're matching pretty well. That's instantaneous bursting, the simplest thing we thought of doing. And in the interest of time, I'll just show very quickly. The next step would be to say, well, really what happens is the bag retracts, and as it retracts, it sheds drops. Well, there's also a theory out there, another full-fledged model with a theoretical representation of what's going on by Wang and Buriba from a few years back. That describes the retraction of the film while drops are shed. And we can do the same thing and apply that type of process on our thin film. So all this is happening at the subgrid level. The cost associated is minimal. And here, so this is still work in progress. That seems to work okay. And we get a drop size distribution for our film droplets that seems to be promising, maybe not quite a perfect match yet. So we're still trying to figure out how to do that well. I'm not going to show this version of the model, but the previous one, instantaneous bursting version of the model. We've applied that on the first case that I showed of this complex air blast flow. And you can see here an instance of a bag bursting. And that gives us this black curve here for our drop size distribution. So this was our experimental PDPA drop size measurements. This was our standard Plick method, and this is with the subscale model. That allows us to account for physics-based breakup of the thin films. So you can see that we've drastically improved our prediction capability with this. So this is, again, there's a lot of stuff we need to understand better with this. I'm not going to claim that this does everything, but certainly it seems that we've taken a large step in the right direction in terms of our ability to predict those flows. Okay, in the interest of time, I don't want to say too much. I'll just say that I've shown mostly a few algorithmic advances that are pretty fundamental in terms of volume of fluid methods. And in the case where surface tension dominates at the subscale, that allows us to probably do everything we need to do in terms of representing what's going on with ligaments and sheets. One of the things we're interested in looking at here is what happens if you have highly viscous or viscoelastic liquids, so complex liquids that you're trying to atomize. They have typically very stable films and ligaments that can stick around for very long times. And so those type of methods might be very, very useful for that. And I'll just show that this is kind of a bag breakup in a Newtonian case. That's what it looks like in a non-Newtonian viscoelastic case. You can see all those meandering ligaments everywhere. And in order to try to predict that, what we're doing at the moment is we're trying to couple that to a microscale solver that actually solves on the 2D manifold immersed in 3D space for the evolution and dynamics of the thin membrane. So here, this is applied to a film, but we're also doing that with liquids. All right, with this, I'll stop. Thank you for your attention. Happy to take any questions, and sorry for being a little long.
Any questions?
Yeah, so the question was, how applicable is it to multi-materials, as soon as we go to more than two materials? It is a harder problem. So typically when you have multi-material reconstruction, you have to say something about the contact angle between them or something like that. And so there's usually pretty crude approximations or logical ways in which you can say, all right, this is the most logical way to distribute the phases. The more interfaces you have, the harder the problem becomes. So I think I'm not overly concerned about, so I think the two-plane reconstruction strategy might be clunky to do in that scenario. I think the PIPIC, the parabolic reconstruction, that we've been kind of amazed at how well it works by just literally splitting the problem into two steps. We first do a standard planar interface reconstruction, and then we force our paraboloid to live in that plane, and we just kind of optimize its curvature. If we break it into those two steps, it turns out there's not a lot of overhead. It works pretty well. And so I think that scenario would probably work almost like plug and play.